Hello, this is Dr. Schleif with another worked example. This one is going to assess your mastery of the learning outcome, state and apply the principle of conservation of momentum in 1 and 2 dimensions. And this, as we can tell by figure 3.1, is a 2-dimensional kind of problem, right? So we've got motion in both the horizontal and vertical axes. If we consider what's going on after the collision, both of the objects, stick together and they're moving vertically here. There's no final X momentum, right? There's no horizontal momentum afterwards. And so that's a nice clue because momentum is always conserved, right? The sum of the individual momenta of all the particles before a collision is equal to the sum of all the individual momenta of the particles after the collision. So before the collision, there's definite sort of X components of velocity. Our job here is to figure out what is the mass of X. Okay, so that's what we're going to try to solve using the clue that, well, there's no X momentum afterwards. And so let's anchor our thoughts on the idea that the initial momentum is equal to the final momentum. And we can apply this conservation law, dimension independent. So all we really are considering right now is just the X component. That should be enough to solve it, because everything that's happening initially with object X is in that horizontal direction. So the final X momentum, that's kind of easy, 0, right? So we know it has to add up to 0. In other words, the component of momentum for object Y that acts in this direction must be the same as the momentum of this object because all of its momentum is directed that way. So this angle here is given as 60 degrees, but if we just sort of resolve this velocity vector, we can sort of see that, well, that's going to be the same angle right there, 60 degrees. And so the relevant trig function here is that the cosine of 60 degrees times the hypotenuse, 9.6 meters per second, would give us the velocity of object Y in the X direction. So however you want to kind of keep track of that, I'll just keep track of it with a vector right there on my figure. So the cosine of 60 is 1/2, and 1/2 of 9.6 is 4.8. So there's 4.8 meters per second of this velocity that's acting to the left. They give us the mass of object Y. So we can kind of think about, well, what's the initial momentum in the X direction? You've got the mass of X times its velocity, which is given 3 meters per second, plus, and again, all we care about is the X component now, right? So we've got the mass of this object, 2.5 kilograms, times its X component of velocity that we just solved for here, 4.8. And again, the units are meters per second. So, and we probably need to make one of these velocities negative compared to the other one, right? Because there's no way to add 2 positive numbers and get 0. It's like one of these has to be negative relative to the other one. And I'll go ahead and make this 4.8 negative. Okay, so I'm assigning left as the negative direction. So this thing is moving with positive 3 meters per second. This thing has negative 4.8 meters per second, because it's opposing it. And that way we can actually get a solvable math problem. 4.8 times 2.5 gives us the momentum of this object Y. So it's 12. So we say, well, what number minus 12 equals 0? Well, it's going to be 12 minus 12 equals 0. And so we can rethink about it like sort of 3 times the mass of X equals 12. So the mass of X must be 4 kilograms. And indeed, if we read through this question paper, it does say, by considering the components of momentum in the direction from A to B, show that ball X has a mass of 4. So they actually give you the clue like, hey, just consider the X component, right? The direction of AB, figure out that the mass is 4, which we just did. So that's nice. All right, the next step is to figure out what is this shared velocity V here, right? So this is similar to ballistic pendulum because it's in inelastic collision, right? The objects collide and they stick together, and so they move with some shared velocity. We usually call it V prime, but they're just calling it capital V here. And so the same way that we just solved that last one, the initial momentum equals the final momentum, but now we're just going to consider the Y direction. So if there is no initial momentum in the Y direction from this thing, all of the sort of final momentum comes from the component of momentum from object y that was acting this way, right? So we sort of resolved our vector and we said, well, we know how much was acting that way, 4.8 meters per second. I kind of prefer to draw the vertical vector over here, so it makes this triangle, but that's the same one as this one. Like it's acting on object y this way, right? There's a component of momentum that's going up. And we can calculate what that is, and we probably should, right? So since it's opposite the 60-degree angle there, we're gonna use the sine function. So the sine of 60 times the hypotenuse gives the y component, or the vertical component of velocity for object y here. The sine of 60 times 9.6 gives 8.31 meters per second. So object y has a velocity of 8.31 meters per second vertically. After the collision, we've got mass x plus mass y, right? Like they're stuck together. So it's some new object that's equal in mass to the sum of the masses of the individual objects, moving at some shared speed v. We know the mass of each one because we already figured out what the mass of x was. If we couldn't figure it out, they told us, show that it's 4. So that wouldn't stop us from solving the next one. So 2.5 plus 4 is 6.5 kilograms times v. And we don't have to really consider the y component of momentum from x because it's moving horizontally, right? So it's like, okay, we could kind of keep track of it if you want to. 0 plus, we need to get just the momentum from object y moving in the y direction. And so that's going to be its mass, 2.5, times the y component of velocity, which we just worked out over there, 8.31. So 8.31 times 2.5 means that 20.78 or so units of momentum were acting vertically from object y initially. Once it crashes into the other object, well, now they stick together. So we've got more mass, more inertia. So it's not going to be going as fast, right? It's going to lose some of that velocity. In the x direction, we just cancel out all the momentum of this object, right? It's kind of like this thing has momentum going this way, but it's just coincidental enough that this has the exact amount of x momentum to perfectly cancel it out. 12 units of momentum. That's how we worked it out sort of a moment ago. 20.78 divided by 6.5. If you guys want to use your calculator, you can. I prefer to do it sort of with mental math. I'll do it to maybe 6-7 decimal places. 3.19763226, I think. Check it in your calculator. I could be off at in the 100 millionths place. Maybe I was off by a little bit, but I'm just going to round it to 3.2. Why not? Just round it there. Just because I can calculate it in my head to 7 decimal places doesn't mean I'm going to record my answer there. It's just like an unnecessary flex there, Dr. Schutz. 3.2. And the stronger flex is reporting the correct number of significant figures. Am I right, class? Yeah, I'll edit in the applause later, don't worry. Last step. Determine the difference between the initial kinetic energy of ball X and the initial kinetic energy of ball Y. So it just wants the difference in the initial kinetic energy. So I'll go back up to the original figure, clear all that working off, and let's just consider this now. We know everything about this object in terms of its velocity and its mass. This one, again, we eventually calculated its mass is 4, but we've got its velocity too. So it's kind of like you just want the initial kinetic energies, the difference between them. I prefer to solve it with a positive answer. So I want to like subtract away the one with less kinetic energy. Can anybody without calculation anticipate which one of these objects has more kinetic energy? Y certainly does, because even though it's less massive, it's way faster, and kinetic energy goes as the square of velocity, right? So it's like 1/2 mv squared. So if you didn't know that kinetic energy was equal to 1/2 mv squared, you'd be at a loss for this calculation. Like it would just be, it would be impossible. So I'm going to set this one as like my first term. So I'm going to say 1/2 2.5 times 9.6 squared minus, I want all that kind of like in brackets, minus 1/2 4 times 3 squared. Kind of like that. So 0.5 times 2.5 times 9.6 times 9.6 again is 100. So this thing has 115.2 joules of kinetic energy. 0.5 times 4 times 3 times 3 is 18. So this object over here has 18 joules. Okay. The faster speed means a lot more kinetic energy, right? And this is that there's a sort of an important, lesson here for young drivers. You double your velocity in your car, you're quadrupling the kinetic energy in your car. That energy is neither created nor destroyed. So it costs you fuel to go that fast, and that energy is still going to be in the universe. Okay, so you have to dissipate it slowly, right? Take care of, speeding. A doubling in velocity is a quadrupling of kinetic energy. A tripling of velocity, like the difference between 20 miles per hour and 60 miles per hour, is only a tripling of your velocity, but you've non-tupled your kinetic energy. Non-tupled. So 115.2 minus 18. For the delta KE, right? We want the difference in kinetic energy. That's going to be 97 joules. All right, this has been a worked example assessing your mastery of the learning objective. State and apply the principle of conservation of momentum in 1 and 2 dimensions with a bonus kinetic energy calculation. Dr. Schleif, still living the physics life. We'll see you next time.